All right, guys, welcome back. And today we're talking about continuity. We're going to start a two-part video series on continuity. And intuitively, continuity just means being able to draw the graph without lifting your pencil. But on the AP exam, you can't just say, I can draw the graph without lifting my pencil, or the graph has no breaks, holes, or jumps in it. You need to explicitly use this three-part definition checklist. First, the function must be defined at C. In other words, C is in the domain. Second, the limit as x approaches C must exist. And third, the limit and function value must equal one another. They must match. Here's just a little GIF showing you a graph where one point is being moved. Whenever the point stops right on the graph, that would make the graph continuous at x equals 2. But if the point were anywhere else, the graph would have a discontinuity at 2. So let's work through an example. Here we have the function f. It's just a polynomial, and we want to determine if it's continuous at x equals 2. The first thing we want to do is evaluate the function at 2 to see if the function exists there. Well, it does. It equals 3, so it's defined there. The second step is we want to evaluate the limit as x approaches 2, and that limit is also 3. Those values match, so the limit equals the function value, so the function is continuous at x equals 2. Here's a picture of the graph with that point highlighted. Now, here's a fact. All polynomials are continuous on their entire domain, which is all real numbers. So if you have a polynomial, you know that it's going to be continuous at any value. Now, let's take a peek at a rational function. Same process here. First, we want to evaluate the function at the x value, in other words, plug in 3. The problem here is that this function is undefined at x equals 3. Well, it doesn't even make sense to go through the next steps because for a function to be continuous, the limit and the function value have to equal one another, but you can't even do that if the function doesn't exist at that point to begin with. So this function has a discontinuity at x equals 3. Here's a graph of the function, and you can see the vertical asymptote at x equals 3. So here's a good tip. Always evaluate the function at C. If the function is undefined at C, then it's not going to be continuous at C. Now, what about rational functions? Here is a rational function f, and we want to know, is it continuous at 0 or 1? Well, first, let's take a peek at x equals 1. The function at 1 is undefined. Therefore, the function is not continuous at x equals 1. We have a discontinuity. At x equals 0, we plug it in and we get negative root 5. So we look at the limit, and the limit is also negative root 5. So the limit matches the function value. So the function is continuous at x equals 0. Here's the graph, and you can see the vertical asymptote at x equals 1, which is where we had a discontinuity, and you can see that the function is continuous at x equals 0. Now, here's the thing. You can't just say the function is continuous because look at the graph. That's not going to be sufficient. You have to use this three-step process. Now let's take a peek at a piecewise function. Let's consider f of x. It's defined in two pieces, and we want to know if it's continuous at x equals 4. So first one, f of 4 equals 10. So the function is defined at 4. Second step, want to evaluate the limit as x approaches 4. We would have to use that first piece. And since the first piece is undefined at 4, we can use the algebraic trick of factoring. So if we factor, cancel out common factors, we get x plus 4, and the limit as x approaches 4 of that is 8. So the limit and function value both exist. However, they are not equal. So the third condition fails. The function is not continuous. It has what we call a removable discontinuity at x equals 4. And here's a picture of the graph. It's a line with a hole in it, and we will call this a removable discontinuity. Here's an AP style question for you. What value of k would make this piecewise function continuous at x equals 4? So remember, we need the limit and function value to exist and be equal at x equals 4. So to get the limit, we take the first piece and factor it, simplify it down, and the limit as x approaches 4 would be 6 in this case. Now here's a graph of the first piece of the function. All we need to do now is just fill in that hole to make the function continuous. Very simple. We just set k equal to 6 to fill up the hole, and the function is continuous. Finally, here's an example where we need to show a function is continuous on a closed interval. Imagine a tunnel arch modeled by the function h on the closed interval -3 to 3. prove that the function is continuous on this closed interval. So here's what we need to check. First, is the function continuous on the open interval, in other words, between the endpoints? Well, radical functions are continuous on their domains, so root 9 minus x squared is continuous for all x between -3 and 3. Then we need to check the left endpoint. So we take the limit as x approaches 3 from the right, and as x approaches 3 from the right, we get 0, so the limit is equal to the function value at -3. And then we do the same thing at the right endpoint. We take the limit as x approaches 3 from the left, and we get 0, which is equal to the function value at 3. Because the function doesn't exist on the other side of each endpoint, we can only approach the limit from inside the domain where the function exists. Now, because the function is continuous on the open interval, and we showed that the function is continuous from the right and left at the endpoints, we can conclude that the function is continuous on the closed interval -3 to 3. Here's a picture of the graph just so you can see what it looks like. Now, here's a big connection. Major AP Calc theorems that you're going to learn require functions to be continuous on a closed interval. So to wrap it up, remember, check the domain first. Watch out for removable versus infinite discontinuities, and always justify continuity using the 3 limit conditions on the AP exam. I hope that video was helpful to you guys. Make sure you hit that like button if it was. Subscribe to the channel as I'll be releasing more AP content. Take care.